Welcome in everybody for another N3AS seminar. Today we're pleased to be joined by Kåre Fridell from Keck, who will be telling us about probes of neutrino mass mechanisms at colliders. So please, Kåre, whenever you're ready, you can share your screen and take us away.
Okay, thank you very much for the introduction. So my name is Kåre. I'm from KK in Japan, and I will be talking about how we can probe the neutrino mass mechanism at muon colliders. And this is based on work done in collaboration with Professor Ruichiro Kitano-san and Ryoto Takai-san, who is a PhD student at KK, and also another work done together with Lucas Graf, Julia Hartz, and Shannon Hatti. Okay, so we know that the neutrino mass is very small, but we know that, of course, it is non-zero thanks to neutrino oscillations. And from different places, we get different bounds on the sum of neutrino masses. So the cosmological bound is the strongest one. However, it's more model dependent than the lab-based searches. And from the lab, the most stringent bound comes from Katrin, who at 90% confidence level say it's below 1 electron volt. So we know that it's very small, but we don't know how small. And if it gets its mass like the other fermions in the standard model via a Dirac term, then this Yukawa coupling has to be on the order of 10 to the minus 12, which is, of course, very small. The smallest standard model coupling is the electron Yukawa, which is at 10 to the minus 6. So there are many orders of magnitude difference. So for this reason and others, it's also interesting to consider the alternative, which is Majorana mass for the neutrino, which would imply lepton number violation at some scale. And so what I show you here are some seesaw diagrams. So the most perhaps conventional ways to generate the Majorana mass is the type 1 seesaw, which uses the same term as the Dirac mass, but also has a Majorana mass for the right-hand neutrino, such that the more massive the right-hand neutrino is, the less massive the neutrino, and that's why it's a seesaw. And the type 2 is similar, but with a scalar. And this scheme is usually thought to imply that we have some gut scale physics, because if we put this right-hand neutrino at the gut scale, it would imply order 1 couplings, which is very nice. But the standard model Yukawas are not all order 1, so there's no a priori reason to assume that. And because this neutrino mass has 2 couplings, it goes as the square of this Yukawa. And if this Yukawa coupling would be around the electron Yukawa coupling, like 10 to the minus 6, it would imply electroweak scale right at neutrinos. So the scale can also go down, even though it's a seesaw like this. Going a bit more advanced, we could also have radiative neutrino masses. And by radiative, I simply mean that there's a loop involved in the diagram. And because there's a loop, it's a closed process. So it can, in principle, have any kind of quantum numbers it wants in this loop. So this can involve things like quarks and leptoquarks and all kinds of particles. Some notable examples, which are maybe the most famous ones, are the C model and the scotogenic model, but there are countless others. You could also keep the seesaw framework, but extend it to a bit more complicated diagrams, so to have more mass insertions, and then, of course, more mediators also. Perhaps most famous in this case is the inverse seesaw, in which you embed a seesaw diagram inside another seesaw diagram, so it's like a double seesaw also. And if you have more waves like this or more loops and so on, that further brings down the scale. So it can be that, like I argued before also, it can be that the new physics scale that leads to Majorana masses for the neutrino are slightly above electroweak or a few TeV or so on. So within the range of colliders, like current colliders or future colliders. And a natural question to ask is then, how would we see signs for this kind of new physics related to neutrinos at colliders. And a general framework to describe these types of interactions is, of course, in the EFT language, where we extend the standard model Lagrangian by a series of high dimension operators. And maybe the most famous one is this dimension 5 Weinberg operator, which simply has two leptons and two Higgs. So if you imagine instead of the blob, this right-hand neutrino mediator, that's simply the type 1c socket. Because it's an operator, it can have any kind of UV completions. Okay, so at the LHC, I think the first process like this that's been studied at the LHC, like lepton number violating process, is the Kyung-Semyonovich process, which you can see here in this diagram. So we have two quarks forming a WR, so a right-handed gauge boson, which can be on or off shell, decaying into a right-handed neutrino and a lepton, where the right-handed neutrino has a Majorana mass insertion and subsequently decays back into a WR and a lepton. And then this WR has to decay into two jets to give us the distinct signal proton-proton into same sign dilepton and dijet. And this signal is the smoking gun of lepton number violation at proton hadron colliders such as the LHC. Beyond this, there's been a more recent study for how we can access this dimension 5 operator that I mentioned on the previous slide at the LHC. And it's possible to do that via vector boson fusion. So in this diagram to the left, the same overall process, proton-proton to same sign dilepton dijet, can instead be mediated via two W bosons, which have a neutrino T-channel exchange. And this neutrino then has to have a Majorana mass insertion in it. And the CMS collaboration did a dedicated analysis for this type of search, where they constrained the mu, so the mu component of the neutrino mass matrix in the flavor basis. They constrained this to be less than 10.8 GeV, which compared to the Catherine bound might not look so impressive, but it can be considered to be a completely separate bound from the Catherine one, because this is for the mu component, not the electron row, which is what they see at Catherine. And for it to be mu, then of course this final state leptons have to be muons, both of them. So dimension 5 is the lowest dimension operator you could have in lepton number violation. Then what we did was to look at the second simplest case, which is then the dimension 7 operators. So we have the same overall process, proton-proton to same sign dilepton and dijet. But instead of having only a single operator, the Weinberg operator, we have many different operators leading to many different diagrams. So I'm showing 3 example diagrams here for some of the operators which are listed here. So if you want me, I can show these explicitly later if you want, but I don't think that's important for the context right now. Just to show you that the scale roughly that we can probe these at LHC is around TeV for most of them. And if the FCC gets built, so that's shown here in the future lambda, we would probe scales of a factor or a few, like half an order of magnitude bigger, generally speaking. There's one operator, ULLD, here that we could probe at 19 TeV at the FCC. And it's notable also to consider the scaling with respect to the this EFT scale. So the reason that it's only a factor few and not several orders of magnitude difference between the LHC and the FCC is that the cross section for this process is very sensitive to changes in the lambda. So for every order of magnitude increase in the new physics scale, the cross section changes by 6 orders of magnitude. And the reason for that is that these are dimension 7 operators, which in the Lagrangian come with Wilson coefficient 1/lambda to the 3. And because cross section is proportional to the square of the Lagrangian, you have 1/lambda to the 6 in the cross section. So that's why we have such a rapid scaling. Right, and because of this, so the constraints we put were close to PV. And the LHC is a high energy experiment where of course the beam has 13 TeV energies. And when we assume an EFT language, what's assumed is that the external energy scales are smaller than the internal energy scale because we integrate out the heavy new physics scale. If this is not true, then the EFT language is simply not valid. And for this reason, we checked whether or not this holds at the LHC for these operators. So taking just an example UV completion model of an operator like this with the 2 quarks and 2 leptons and a Higgs, we compared how our EFT approach, the constraints we get using our EFT approach compares to this simplified model. And as we can see in this figure, for high mediator masses, the approaches agree quite well, which is what you would expect from an EFT. The EFT assumes that you have a high scale that you integrate out. But as we approach the smaller masses, they start to differ, where actually this EFT estimate slightly underestimates the real constraint, so to say. And at some point, we hit the minimum mediator mass around a TeV, where under which the partons that are coming in have a higher energy on average than the mediator. At this point, we don't feel comfortable using the EFT. So this was about the LHC and a little bit about the FCC. Of course, what we get from this analysis are constraints and not discoveries, because the LHC has not discovered this process. But because we're interested in really what is the physics behind a neutrino mass, we want to know how could we potentially in the future really discover the new physics. And for that reason, we have to look at new colliders such as the FCC, but there are also other options. And yeah, so like I said, the FCC is a proton-proton collider, as we all know. There's also, you could also build, for example, a linear electron-positron collider, such as the ILC, which was receiving a lot of hype in Japan, but perhaps less so in the last year or a few years or so. But it's still not quite decided what's going to happen with the ILC. And there's also maybe in the last few years, there's been a revived interest in a third option, which is the muon collider. So we don't know. I mean, we don't know what we're gonna get if we're gonna get any of these three. So it's interesting, of course, to study all of them. But what I will be from now on focusing on today is the muon collider option. And one of the main reasons that we are interested in muon colliders is the proposed muon collider experiment mu-Tristan, which would, if built, be at the KK site, so where currently the super KKB accelerator is. So we wouldn't have to dig any new tunnel or anything. Actually, if you remember the Tristan experiment, which was there before KKB, which then became super KKB, it's named after this simply. So it would use the same storage ring also as Tristan. And what else we can recycle is the muon cooling technology, because I don't know how many are aware of this either, but in Japan they are building an experiment to test the muon G-2 anomaly that's been found in Brookhaven and Fermilab. And the way that they are getting their cold muons can be also used for this collider. So what would happen is that we have a proton beam that gets smashed on a target to produce a bunch of pions, and the pions are collected and they're stopped by a series of tungsten foils, and after they stop, they decay into muons. And on the sides here, we have a bunch of free electrons that catch the muons, forming muonium. And in that way, they stop the muons there. And the muonium can then be ionized with lasers to produce a bunch of cold muons. And it's this then compact bunch of cold muons that can be re-accelerated in linear accelerators and then injected into this ring that will serve as the mu-Tristan experiment. And this cooling technology only works for mu plus so which maybe some people would call anti-muons. It does not work with mu minus for several reasons. One of them being that you can only catch the plus with electrons to form muon. I mean, to make muonium out of mu minus, you would need positrons, which are of course not available in the same quantity. But so we would collide at mu Tristan mu plus with mu plus, but you could also run it in the mu plus with E minus mode. So it would serve both as a positron muon collider and a muon muon collider. And the types of searches that can be performed are both the EFT searches that I talked a bit about earlier regarding lepton number violation at LHC, but you could also search like at LHC for any kind of models. For an example here is shown for dislepton production or muon maybe, which they would be able to probe around a few TeV masses at mu Tristan. And for the effective field theory case, as an example here is shown the elastic scattering mu plus back into mu plus, which is of course a standard model process, but you could look for deviations from the standard model cross section. And in this, you would be able to constrain the operator scales to at around 100 TeV when the experiment is running at 2 TeV center of mass energy. So you see here we have a quite large splitting. The constraints on the lambda that you get are 2 orders of magnitude greater pretty much than the center of mass energy. And this makes it so that this validity of the EFT isn't as much of a concern. It's for sure valid if it's several orders of magnitude higher than the energy, the scale of the experiment. So for this reason, muon colliders or mu Tristan specifically is very well suited for studying these kind of effective field theory operators. And in the past months, there has been some papers or quite a few papers that's come out, like phenomenology papers looking at specific modes or specific searches one could do at mu Tristan. So I'm showing some diagrams here related to the physics of neutrinos and neutrino masses. In the top here, you see 3 diagrams where this neutral scalar H is produced, where this H can be part of the Z radiated neutrino mass. And you can see that these authors have considered both mu plus E minus and mu plus in the initial state. You could also search for WIMPs, like dark matter, either via corrections to the T-channel mediator in elastic muon scattering or via the production of massive WIMPs in the final state. With regards to the lepton number violation, I showed you earlier that we have this series of actually odd mass dimension operators only to describe lepton number violation. So the simplest process to look for, or the simplest operator to look for at mu Tristan is the dimension phi 1, which can lead to mu plus going into W plus. And this is, of course, a smoking gun signal for lepton number violation. However, similar to how CMS found 10 GeV constraint on the neutrino mass, we would again here find, we would be very far away from the actual neutrino mass scale if we look for processes like this, because if you flip this one on its side and consider the Higgs instead of the Goldstone modes that become the W's, this is a neutrino mass diagram. And so we know that this is proportional to the neutrino mass. So we know that it's small. But there are other lepton number violating processes we could look at, such as, for example, the dimension 7 operators, which don't necessarily have to exactly be proportional to the neutrino mass. However, again, as we saw earlier, these kind of processes are suppressed by 6 orders of magnitude of the new physics scale because they come from dimension 7 operators. A related process is lepton flavor violation, which can be mediated via these dimension 6 operators. And actually, this is wrong. The Wilson coefficients have mass dimension -2, actually, if the operator is dimension 6. So the cross section for these processes are suppressed by 4 powers of the lambda. So they should be less suppressed than the lepton number violating modes. And what I would argue is that if you have Majorana neutrinos that are generated by some new physics, new couplings to leptons because the neutrinos are part of the standard model lepton doublet. You know that any interaction that they have, if you're invariant on the standard model, would also appear in the charged leptons. And there's no reason to assume that this coupling is exactly diagonal with the masses, that they are diagonalized in the exact same way as the things. That would be very weird. So therefore, it would naturally lead to lepton number violation. So we can then assume that if we have some new physics that leads to Majorana neutrino masses, they would also be lepton flavor violation. And so what we study in this work is therefore the lepton flavor violating signal in neutrino mass models. And there is an ongoing work to also look directly at lepton number violation in Mu-Tristan, but I won't be talking more or much about that today. So the lepton flavor violating signals can be mediated via these dimension 6 operators or the 4 fermion operators, which just look like this, but you have different flavor indices on the leptons and different projection operators. And the same term that leads to the process mu plus going into mu plus tau plus would also lead to the tau plus into 3 mu decay. It's simply putting tau mu indices on these leptons. But they depend differently on the projection operators. And so we want to see if Mu-Tristan is actually more sensitive to these flavor violation than already currently existing bounds are. And to compare these two processes directly, we form this ratio of chiralities, which is simply proportional to the cross-section for the Mu-Tristan mode with this rare tau decay. And when we parameterize it like this, we see that the number of events we would expect at Mu-Tristan for an energy, center of mass energy of 2 TeV and an integrated luminosity of an inverse Autobahn is almost 8,000 events, assuming that this branching ratio is close to its current experimental limit. So based on this, we can see that Mu-Tristan should be a very good probe of such lepton flavor violating physics. So that was for the specific tau to 3 mu decay. There are also many other rare tau decays that they've actually constrained at Bell, for which if there's a similar story, we would expect a few thousand events. There is the most sensitive probe of lepton flavor violation. There are two modes. There's the mu to 3e and the mu to e gamma are the most sensitive modes here, because this is a 4 fermion process. We are looking now at the mu to 3e. For which, if the corresponding chi parameter would be equal to 1, you would expect 6 times 10 to the minus 2 events. But this is a bit misleading, because of the mass splitting between the first and the second neutrino mass eigenstate, you would actually expect the chi parameter to be almost 2 orders of magnitude, like almost 100 or at least 30 or something. So this number would then increase, and all these numbers I'm showing here also depend highly on the lightest neutrino mass M1 and the amount of CP violation that you have. So I will talk more about this later. But in the future, these modes will receive more constraining limits from Bell 2, in which case we would only expect 100 or so events. So what this tells us is if they see any of these modes at Bell 2, it would be a good motivation, very good motivation to build a Mu-Tristan. So as a quick UV completion example, we studied the type 2 CISA model that I mentioned earlier, in which case we have a triplet scalar that gives mass to the neutrinos that gets a vacuum expectation value in its neutral component. And the neutrino mass matrix that you get then in the flavor basis is diagonalized by the PMNS, which I show explicitly here because I will be talking about these angles later. So we have the Dirac CP violating angle, the delta CP, and there are also 2 Majorana CP violating angles, which cannot be constrained in neutrino oscillation experiments, but I will show later how they can be constrained at Mu-Tristan. So this type 2 CISA model leads of course, to the lepton flavor violating scattering, but also to the lepton number violating scattering I mentioned earlier. And if you look at these cross sections, you see that the cross section for the flavor violating mode depends only on the Yukawa couplings, while the lepton number violating mode depends on the neutrino mass matrix. Because, like I said, this is really a neutrino mass diagram. So we know that this crossing cross-section has to be very small because the neutrinos are very light. But there's no reason to assume that these Yukawa couplings are small. The neutrino mass could be small because, for example, because the VEV of the delta is very small. So this matrix need not be small just because the neutrinos are very light. And that's a good reason to like I said, to look for flavor violation. So in our old EFT language, now only the left-left operator is non-zero because the delta talks only to the left-handed leptons. So this chi parameter, what I introduced, can be written as a fraction of entries in the neutrino mass matrix in the flavor basis. And we will now define a scale lambda at the central values of all the PMNS mass splittings and angles, just to have a scale to talk about, and because it depends highly on these values. And using this scale, we can express the number of events as shown down here. So if we have the central mass energy 2 TeV, and for one inverse autobahn integrated luminosity and a new physics scale at 34 TeV, we would see around 100 events. So we would expect to be able to probe new physics scales related to the neutrino mass generation around 34 TeV for a wide range of different flavor components. So I'm showing here mu tau as an example, like I said earlier, but of course it can be done for all the other flavor components, including the mu tau tau, which cannot be probed in tau decays. So that's actually a completely unconstrained parameter. It leads also to the elastic process, the type 2 seesaw, the mu to mu. And it turns out that because we have an interference with the standard model, this process, the scale that we probe in this process is actually higher than the previous ones. So we can probe scales, like I showed you earlier, these operators were actually for this process. So at around 100 TeV, we could probe the scales. And this is then the type 2 seesaw scale, right? That we're probing at 100 TeV, but only for the 4 mu components. So summarizing these different flavor violation searches, we see that the dot dashed line here, the elastic scattering, is the best probe actually, although only for the mu and mu component. Then we have the mu-Tristan searches for this process, mu to mu tau, which are really good probes. And all the flavor violating decays are shown here in different colors. And here the most, like I said in the beginning, the most sensitive probes are mu to E gamma and mu to 3E. And on the x-axis, we have the M1, the lightest neutrino mass. So as we can see, these constraints depend highly on this parameter because they have different flavor components, so they depend differently on the PMNS matrix. And this is simply the reason. Now, coming to the Dirac violating CP violating Dirac angle, we can see here that the number of events you would expect at mu-Tristan varies highly depending on the value of this parameter. So in this plot, we have fixed the new physics scale such that it generates this mu to 3E decay at its experimental limit. So if the real branching ratio is close to the experimental limit, you would expect several hundred events at mu-Tristan for non-trivial values of this angle. And the examples I showed earlier were all for delta CP equals 0, where you would expect not so many events. So the point here is that it changes highly depending on this angle. And if you know more about the model you're looking at, then this can be used to actually constrain the value of this parameter, hopefully. The same goes for the Majorana angles. What's shown here is the cross-section, the ratio between the cross-sections of mu to mu tau and the mu to tau tau for different values of M1 and the Dirac delta CP. And as can be seen, this ratio of cross-section can change by about a factor 5, depending on what are the values of these Majorana angles. And so if we would observe several different flavor violating modes at mu-Tristan, we can use the ratio to get a hint about what these angles are. Yes. Okay, that was it. So we've seen that you can use these effective operators related to neutrino mass, or you could probe them at the different colliders. And new physics related to the muon and neutrino masses can also lead to short lepton flavor violation. And mu-Tristan, the proposed muon collider experiment at KK, will be able to probe new physics scales related to these processes up to around 100 TeV and also constrain the different SCP angles. So thank you very much.
Thank you, Kåre, for the very nice talk. Do we have any questions for our speaker? If so, please raise your virtual hand. So I was curious when you were discussing, I think you had the table of, the different flavor violating limits and what the expected, exactly. So you have the expected number of events at mu-Tristan. So I'm curious because I thought that when you were discussing this was model independent, right?
Mm-hmm.
So I'm curious why, if you're thinking about like mu to 3e, so you're in the mu e flavor component, why does that necessarily give you something in mu tau?
Right, so it's model independent in the sense that we have EFT operators where we don't assume which new physics is generating them, but it's model dependent in the way that we assume that these operators lead to the neutrino mass. And
okay.
in that way, you don't know the value of the couplings, but you know the relationship between the different couplings because of the constraints on the PMNS matrix. So what we assumed in here were the central values of all the PMNS angles and so on,
Mm-hmm.
and a massless lightest neutrino also.
Very good, thank you. And does could mu-Tristan look for mu plus E plus final states as well?
Yeah, certainly, mu plus E plus. So yeah, I mean, any kind of final state you imagine can be searched for. Of course, anything to do with electrons has already or will generally be more already constrained, but certainly. And the initial state here we've been only looking at mu plus initial states, but you could also have, of course, electrons in the initial state leading to different operators being triggered also.
Great, thank you. I see we have a question from Lukasz.
Yeah, there is a few of us here in San Diego watching this actually, and George has a question.
Thank you for a very nice talk. Good overview. My question is this. I mean, if you put constraints on lepton number violation among the charged leptons, can you translate those constraints in, at least within these models, into constraints on lepton number violation among the neutrinos?
So it depends on the kind of operator. So lepton number violation in the charged leptons would be constrained by, for example, neutrinoless. No, that's not true. That's model dependent, but it can be probed at neutrinoless double beta decay. It can also be probed at LHC. So your question is if this directly translates to the neutrinos, right?
I'm sorry. So you have constraints that come from accelerator-based experiments.
Yes, yes. So we have.
If you have,
okay,
and then in a particular model, those constraints have some meaning for the neutrino lepton number violation. Is that correct?
Yes, it's correct if the leptons that are involved come from the lepton doublet, like that you can think of in an EFT language. So I think, there's enough to show one operator, which I actually had as an example here. So this operator, for example, the QULLH, is a standard model invariant constructed with standard model invariant fields, and this involves the lepton doublet. And inside the lepton doublet, you have both the charge and the neutral leptons. So if this is the operator that's responsible for your lepton number violation, it necessarily also is lepton number violation in the neutrino sector. Of course, you can construct these operators using only the singlet, right? The charged lepton singlet, the right-handed one. Then there is no a priori reason that they directly go into the neutrino sector. However, even if you have such an operator that only involves the charged singlet, you can construct using W loops. You can construct a neutrino mass diagram with this one. So whichever operator you have that has delta L equal 2 would in some way lead to, or would lead to a neutrino mass at some level, not necessarily the observed one, but it would affect the neutrino masses.
Thank you.
No.
Do we have any other questions for Kåre? If not, let's thank our speaker again. And I can